So what are the two most abundant elements on Earth? Any idea? No. Yes, that's right. Silicon and oxygen are the two most abundant elements on Earth. Now, if you take silicon and oxygen and put them together, do you know what you get? You get something that everybody has seen, I think. You get quartz. This is a sample of quartz. And it's made up of silicon and oxygen. There's various different types of quartz, different colours, mainly due to the impurities that are present in them. And they come in lovely shapes often, that you usually find not out in the real world, but you usually find them in hippie shops, giving you all sorts of healing properties. You normally find it in this sort of amorphous form, or looks like an amorphous form, lying around the bush. Okay, so this is quartz. It's made up of silicon and oxygen. One silicon atom and two oxygen atoms. That's all it is. That's what quartz is. Now, if I take the silicon and oxygen and add a few more silicons and a few more oxygens, but also add some potassium and some aluminium, not quartz anymore, it's called feldspar. Now, if you change things around a bit and add a hydroxide and a few other of those elements, you end up with this collection of atoms. And it's no longer quartz, it's no longer feldspar, it's in fact this, which is what we call mica. There are two types, there's biotite mica and muscovite mica. This is muscovite mica, and it's quite a beautiful thing because when you look at it closely, you can see through it. You can see me through it there. Hello. This stuff was used, you might, if you've got a very old wood heater at home, or you see a very old wood heater, you look closely at the door, the glass. It's not actually glass. The very early ones were made up of this stuff called mica because it's see-through and it's heat resistant. Okay? When we started to get heat resistant glass, then we replaced all those mica glass, those mica doors in wood heaters. Anyway, I digress. So you have this collection of atoms, you end up with something called mica. Now, all of these things, mica, feldspar, quartz, and a whole lot of other things that a whole lot of other different arrangements of atoms, we call minerals. So you've heard of minerals? Well, this is what a mineral is. And there are hundreds and hundreds of different types of minerals. So these are not rocks. We call them minerals. And minerals have these properties. They have a characteristic chemical composition, which is why I started out showing you those different arrangements of atoms, elements, give us these different minerals. So silica and oxygen gives us quartz. Change the elements, change the atoms, and you change the mineral. So they all have a characteristic and unique chemical composition. They are crystalline in structure. So you can have crystals like this fancy one, or you can have crystalline structure like we saw before. There's a different type of crystal, see-through one, very thin, very flat. This sample here of quartz, although it looks sort of lumpy and you can't see very much, if you would look closely at it under a microscope, you would see, particularly an electron microscope, you would see that the atoms are arranged in a nice way that gives you a nice crystalline structure. Okay, so they're chemical composition, unique chemical composition, and they need to be crystalline in structure, and they're always solid. Okay, so these are minerals. They are not rocks. Don't go out into the bush and pick up some quartz and throw it at somebody thinking you're throwing a rock. You're not. You're throwing a mineral. But rocks are made up of minerals. And the first rock type we're going to look at is an igneous rock. So igneous rocks coming from the Greek meaning ignite or fire, are made up of these minerals. How does this occur? If you melt these minerals, they will form what's known as a magma. So we often say magma is molten rock. Well, actually it's molten minerals. It hasn't been formed into a rock yet. Okay, so it's not even molten minerals because a mineral has to be a solid. So the material we call magma has these collections of liquid arrangements of atoms. Now, different magmas around the world will have different elements in it, and that's what gives us different rock types. Now, molten material, the type of rock that it occurs is called an igneous rock. And we will look at the different types of rocks. There are 3 rock types: igneous, sedimentary and metamorphic. And we're going to look at igneous rocks first. But let's just quickly look at the relationship between minerals and rock types. Now, let's have a look at, if we have a magma that contains quartz, feldspar, and mica. Okay, so here are these 3, and if we then melt those minerals together with a bit of fire, like that, eventually when this molten material then becomes solid again, we end up with granite. And if you look closely at granite, you can see very closely, you have the pink feldspar, you have the whitish greyish quartz, and in this case you've got the black biotite mica. In other cases you'll have the very shiny muscovite mica. So rocks are made up of minerals. Okay, this is a rock, these are minerals. Okay, so granite is an igneous rock. Igneous, the word igneous comes from ignite, which means from fire. So it's the melting of that material, then cooling and becoming a rock. But sometimes you get this rock called rhyolite. Now, it has the same minerals in it. It has feldspar, quartz and mica. But for some reason it doesn't look like granite. It's the same makeup of minerals, granite and rhyolite. They have different rock names. How can that be? Well, we need to think about crystal formation. So, as we saw, all minerals form in a regular pattern that we call a crystal. But they need time to grow. And that time comes from the rate at which the molten material cools down. If it cools down slowly, then the crystals will have time to grow. And this is a great example of huge crystals occurring where the minerals have been allowed to cool very, very slowly. So if they've been allowed to cool slowly, then the crystals will have time to grow and you'll end up with large crystals. This lumpy rock here, we say this is a crystalline rock because we can see the different crystals. We can see the quartz, the feldspar and the biotite with our naked eye. So we can see the crystals. So we say this is a crystalline rock. So it must have cooled relatively slowly. This rock, this rhyolite, with our naked eye, it just looks like a uniform surface. With a very powerful microscope, we can see the different crystals in there, but with our naked eye, it just looks as though it's got a uniform surface. So we say this is a non-crystalline rock. So this must have cooled really, really quickly. So the crystals started to form, but then they were sort of snap frozen before they were able to get large enough. So the key concept here is that large crystals are a result of slow cooling and small crystals are the result of fast cooling. So where does that occur? How can that be? How can you get different rates of cooling? Well, it's relatively simple. As magma rises through the asthenosphere and into the crust, it sometimes gets stuck under many kilometres of rock. And that kilometres of overlying rock acts like a blanket and keeps that magma warm for longer. It insulates it. It insulates it, essentially. It can be 1,000 degrees centigrade in the asthenosphere, but it's only 15 degrees on the Earth's surface. That's a huge difference. So if it stays hundreds of degrees warmer, it's going to cool more slowly. That's going to allow the crystals to grow larger. And so you end up with a crystalline rock like granite. But if the magma material comes out onto the Earth's surface, where it's only 15 degrees on average, that's so cold that the rock will cool very, very quickly, and the crystals won't have time to won't have time to grow, and so will be very, very small. Pretty simple. Now, sometimes you get a rock that looks like this. It's got large crystals and small crystals. Now, that's a bit problematic. How can that be? How can you have evidence of two rates of cooling? Well, it happens like this. Firstly, the magma rises and it gets stuck for a bit, and so it starts to cool. And so while it's cooling under the Earth's surface in that insulated part of the crust, then those crystals will start to grow, and they'll have time to grow and become solid and become quite large. But the rest of it will stay molten because it hasn't reached its solidification temperature, or essentially its freezing temperature. And so what happens, okay, so that was fine. And if it stayed there, then all of those other minerals would cool and become solid and have relatively large crystals. But what's happened to get a rock that looks like this, with large crystals and small crystals, that halfway through the cooling process, some tectonic forces have occurred and pushed up that magma onto the Earth's surface, where whatever wasn't solid before is now snap frozen with very small crystals. That's how you get large crystals and small crystals. And we call that a porphyritic rock. All right. Let's have a look at another collection of rock-forming minerals. Let's say we have this one called olivine. It's got a nice sort of greeny colour to it. We have something called pyroxene, which is this sort of blacky one. We have another one called amphibole, which is a black one. All right, and we'll have some small amount of this feldspar. Now, if you take these rocks and melt them together, add that fire again, it melts into this rock here, which is basalt. So different minerals together, melting together and forming a rock, will give us, with that collection of rock-forming minerals, these new ones that you've come across. So you've heard of feldspar, but now we've got olivine, pyroxene, amphibole coming together will give us a different rock type. Now, is this rock type crystalline or is it non-crystalline? Well, I can't see any sparkly bits in it, which would indicate that it's got some crystals in it. So this is a non-crystalline rock type. And so this must have cooled very quickly. And of course it does very commonly as it comes up those mid-ocean ridges to the Earth's surface pretty quickly. And yes, it's under the ocean, so it cools even more quickly. That's why you very rarely find crystalline basalt, which of course isn't called basalt. We call it gabbro. And this is an example of gabbro. Okay, so we know where basalt comes from because it comes from the asthenosphere and mid-ocean ridges. Where does granite come from, you may be wondering? Well, remember when we looked at subduction zones, and as the material, the oceanic crust went underneath the continental crust, some of the oceanic crust melted, it rose, the heat of that molten material melted the continental crust around it and resulted in volcanoes with granitic magmas. That's where you get granite coming from, or rhyolite if it cools very quickly. Okay. All right, let's have a quick look at different types of volcanic landforms. So there are different types of magma. So we've looked at magma that becomes basalt and magma that becomes granite. Um, when you look at magma as it comes out onto the Earth's surface, we then call it lava, and it has a couple of different properties. Sometimes the lava will flow really quickly, like this, and sometimes it will flow really slowly, like this. What's causing the difference? You might think it's temperature. It's not actually, because they're both about the same temperature coming out of the Earth's surface. The key difference between these two magmas is that one has low silica content and the other has high silica content. The amount of silica that's in a rock type or in a lava will control how viscous it is. So a high silica will result in high viscosity. Low silica will result in low viscosity. So granite, remember granite? I talked about quartz being in granite. Well, I didn't talk about quartz being in basalt. So quartz is very rich in silica, and so granite contains quartz, and so that creates its viscousness, its high viscosity. Whereas its absence in basalt means that it is low viscosity. So it flows more easily. Basalt flows much more easily than does granite. Now this has an impact on the types of features that we get as a result of these magma and lava processes. So the first feature we're going to look at is what's known as a pluton. This is a great example of a pluton. This is Mount Buffalo in northeast Victoria. It's a huge lump of granite. Why is Mount Buffalo made up of granite? The reason is it was that part of northeast Victoria was at the edge of a subduction zone hundreds of millions of years ago. And as that subduction zone occurred, this granitic magma came up. But it was so viscous, so high in silica, that it didn't, and perhaps the pressures weren't as great, that it didn't make it to the Earth's surface. And so it stayed under many kilometres of rock, underneath the rock, and so cooled very slowly. And if you ever go to Mount Buffalo, you'll see that the crystal size is quite large. So it cooled very slowly. Now eventually, as this diagram shows, those kilometres of overlying material eroded away over many millions of years, leaving this exposed granite on the Earth's surface. All right, another type of feature that you can find is dikes and sills. So this is a good example of where molten material has risen, but it hasn't come up in massive forms. It hasn't created a volcano, but has moved up enough to form into cracks in the Earth's crust. Okay, so a dike is where it's vertical, and a sill is where the crack has been horizontal. And some great examples of that are at the Warrumbungle National Park in New South Wales. And this photo here is of the bread knife, and it's a good example of igneous material that has risen up through a very thin crack in the Earth's crust, solidified. Crystal size is probably moderate, it's probably quite small because it was a small amount of magma, so it probably cooled pretty quickly, but you might see some small crystals. And then all the material, all that other rock has been removed, and it was soft because it was softer, leaving this very hard igneous rock behind. Alright, so they're our below ground formations. Let's have a look at some above ground formations. Now one way you get above ground formations is from lava flows. And as the lava flows across the Earth's surface, and it'll flow over very large areas of the Earth's surface if it's a non-viscous material, which is what? That's right, it's basalt. And there's some great examples in Western Victoria of large lava fields made up of basalt. That part of Victoria also has volcanoes, which we'll look at in a minute. But large areas of large cracks in the Earth's surface opened up, and lots of lava came out onto the Earth's surface and spread out onto the Earth's surface, and it's creating pretty good soils as well, some nice dark, rich soils. So that's the big lava flow. If the lava flow is not quite so so thin, but it can actually build up to quite some thickness, and so you end up with this effect of this very thick lava flow. As it cools, it forms into these hexagonal formations, if it's allowed to, if it's not much disturbance, and you end up with these classic columns, often called Devil's Walkway or Devil's Staircase. But the biggest, or the most common way, or the most obvious features you get above ground are, of course, volcanoes. So let's have a look at some of those. So Australia is often said to be very tectonically stable, and indeed it is. We don't have any active volcanoes, except for one. Where is Australia's only active volcano? That's right, it's on Heard Island, and the mountain is called Big Ben, and here it is. It happens to be in the Antarctic province of Australia, 3,000 kilometres southwest of Perth. But nonetheless, it is an active volcano. But no, there are no active volcanoes on the mainland or in Tasmania. However, there were lots and lots of active volcanoes over time. And this diagram just shows you where the main volcanic fields are. They are pretty much in that eastern part of the continent, down the east coast extending into South Australia. Let's have a look at different types of volcanoes. So let's start with a shield volcano. Now a shield volcano is usually very, very broad and has very shallow slopes. And the reason is because the type of magma that comes out is very low in viscosity. So it flows very quickly. And these form very large, broad volcanoes. Some good examples in Australia is Mount Canobolas near Orange, which you can sort of, doesn't look like much these days, but if you put the original Earth's surface over the top, this is what it would have looked like, or this is an outline of what that particular volcano would have looked like. The next one is Ball's Pyramid, which is near Lord Howe Island. And Lord Howe Island itself is an old volcano. Ball's Pyramid is just the last bit of the edge of it that's being eroded away into the ocean. And Mount Warning up on the border of New South Wales and Queensland is another example of an old shield volcano. It's very, very large and is very, very extensive, and it's weathering away into some fabulous formations and national parks up there. Other types of volcanoes that you can get are cinder cones. And cinder cones are formed by this explosive nature of magma that's thrown up into the atmosphere in very fine particles. It cools and comes down as cinders or ash and builds up quite steep slopes because it's just falling down and building up a steep, quite small, but steep sloped volcano. And there are some great examples in eastern parts of South Australia and Western Victoria, such as Mount Shank, Mount Noorat, which you wouldn't really know unless you sort of flew over them sometimes, but they can be, but you can still see them. Some of these are quite young, in fact, so young that some indigenous stories talk about in their dreamtime and legends about exploding, or talk about them in ways that indicate that they probably were volcanoes occurring that people observed 40 or 50,000 years ago. Another type of volcano is known as a composite cone, which is made up of alternating bands of ash and then lava forming in this sort of pattern. And that mountain, that volcano we talked about before, such as Heard Island, Big Ben on Heard Island, is a composite cone. Usually very large volcanoes. Another above ground feature is a caldera, which doesn't quite make it into a volcano because as the pressure rises and the magma comes up, the earth cracks and releases much of that pressure. So rather than forming into an explosive or into a volcano that then spews lava onto the earth's surface, the pressure is released, so there's insufficient pressure, the pressure is released and then the pressure stops and as the magma cools and shrinks, then the overlying surface of the earth falls down along those cracks and forms what is a lower part in the landscape that often fills with water. There's some good examples in Victoria, such as Tower Hill. So you can see the outline there is the caldera, and then there's been a a subsequent rise of more magma up in the middle of Tower Hill. Blue Lake is another example of a caldera. The myth about Blue Lake is that there is no bottom to Blue Lake, it just goes all the way to the centre of the earth. No, it's not quite true. But what it is just a very deep lake, and the bottom of it is not uniform, so every time somebody goes and does a measurement, they find a bit that's a bit deeper, so they just assume that it goes all the way. Quite sure of that logic. Now, most of these volcanoes are not the result of plate boundaries. Okay, so Australia is, and has been for tens of millions of years, very tectonically stable because there are no plate boundaries, certainly no plate boundaries currently on the continent of Australia. As it broke up, sure, there were, right? And as we saw the breakup of Gondwana, then that was demonstrating where plate boundaries occurred. But these, and because there would have been huge volcanoes then, but currently, which have all been, eroded away and lost, because it's been millions of years since they occurred. But all of these volcanoes that we've just looked at are quite recent, and they are the result of what's known as a hotspot. So what happens is that as the plates move, they move over hotter parts of the mantle, and it's those hotspots, those hotter parts of the mantle become more active over time, and then become less active and more active and less active. When they're very active, they can push magma up through the Earth's crust and break out onto the Earth's surface in these different types of volcanoes. And what's interesting is that you can see how the continent has moved, moving from south to north, and so that hotspot has moved. It hasn't moved at all, but it appears to have moved north to south. And if you date those volcanoes down the eastern side of the continent, you find that the older ones are in the far north and they get progressively younger, which is an indication that the plate has moved over the hotspot and has become active, producing these volcanoes or lava fields. Currently, the thinking is that the hotspot is perhaps somewhere underneath Melbourne or Bass Strait or Tasmania, and may of course become active again, who knows. Okay, so that was our introduction to igneous rocks and volcanic landforms.